Hello. What you're about to see is a demonstration of a tool that's been years in development by Greyrock. This tool is a discrete event simulation that allows any printed circuit board factory, regardless of the number of products that you have, regardless of the complexity of the routing, be it military or an automotive product, regardless of the type of equipment configurations that you might have for presses and drills and other pieces of equipment, you can precisely determine your opportunities for improving your printed circuit board operation. This is very exciting to be able to have this technology today for use by any printed circuit board shop. For this video, we are going to look at 4 scenarios. 2 one-product scenarios and 2 two-product scenarios. Let's begin. Welcome to the Factory Activities Simulation Tool Analyst, or FASTAnalyst. What you are seeing right now is one job of 16 panels going through a 51-step routing. You see the whip levels in the green bars, but wouldn't it be nice to be able to see what the process steps were? And there we see the 51 steps in terms of their location. And this table shows the 52-step routing. So what is FAST? It is a discrete event simulation of your printed circuit board factory. And what does that mean? You can load in specific plant data and see what happens. And why use FAST? Well, what we're going to see in this first scenario is we're going to determine the plant's capacity for this 51-step product. One of the things we can look at is the time utilization. So this shows the whip levels, and this graph shows the time utilization. So the question is, how much more product can we put into the factory? So if we look at the current schedule, we're running 8 jobs where there's 16 panels per job. Where there's 2 cores, and we're releasing this schedule once every 8 hours. To change this schedule, we simply are going to double the number of jobs. So I'm going to go from 8 to 16. So let's run this second scenario. The first scenario was where we had half the demand. We see immediately there's a likely issue in press. Let me show you the production graph. This graph shows that the cycle time is increasing without bound. That's not a good situation, because that means whip is accumulating in the plant. And though you could block the whip from going into the plant by using some sort of con-whip strategy, bottom line, you're taking in more demand than you can satisfy with your customers. So if you do that, you're simply just going to increase the number of back orders. And we see that this has become a true bottleneck, and we can validate that by looking at the utilization of the whip. We also can do something else. We can isolate on this. So let me pause the simulation for now. And what this shows here, this 1.27, that's 1,270 pieces. That's way too many. But let's isolate. And so I'm going to open up this other table. And I am going to select pre-clean. And I'm also going to look at the press. I also want to look at something else. I want to look at the utilization. And I think I also want to look at electrical tests because that utilization is pretty high, as is image. But I'm just going to look at electrical tests for now too. So that's index number 29. We'll go here. And now when we do this and we get this running again, we see this, but if I turn animation off, you see we're only looking at those items. So we can be very highly selective in this graphic. And let's put the routing back on underneath. And this really shows clearly that we need to do something about these presses. And we can let this thing run, which we'll do to the end. And when we reach the end, we can store the results of this scenario by hitting the Save To button. And we see that we're able to increase the throughput to 19.09 panels per hour, but we have a cycle time of 123.8 hours versus the first situation where we had half the demand with a throughput of 15.36 panels per hour and a cycle time of 17.62. Now, I don't know about you, but I didn't like those results. Let me show you something. Let's look at the specs list. This is the specs list for electrical test. And what this shows is two products and the cycle and the fact that one tester gets one panel, that's number in the stack, and each test machine and the process time for each test machine. You can see the same type of thing in lamination. So if I go to the lamination index, which is 13, and I look at the spec list, and what we see is for the medical product, which we're going to show shortly, it's only valid on press 3 and on press 4, not on press 5, and not on press 2 or press 1, and that's for trip number 1, but it only goes through lamination once. If you look at the HDI product, the high density product, which is the one that we're running, it's valid on all presses for the first lamination and the second lamination, but you can see by just making these selections, you can be highly specific of what product can go on which machine, what product can be mixed in each machine based on the cycle. We're not going to get into that right now in terms of the details, and what the process times are. So it's this kind of detail you can get into this model and have it really reproduce your factory. Now, there's even more. If we look at the department settings, we see that we have 3 presses available where we have 4, 5, and 4 slots. Now you might ask yourself, well, how much product can you get into each slot? Well, that's where we return back to the specs list, and we see that the number in the stack in each of those press openings is 5 for the first trip, but when it comes to the second lamination, you can only get 3 panels. So again, all the bases are covered in the simulation model. It is rather incredible. So I'm going to add 2 additional presses, and let's run this thing. And you can see how the utilization finds its own level. Things are looking pretty good. Let's see how the whip is doing. Whip looks like that's doing well. Let's look at the graph. The graph looks like it's doing well. We're also going to look at something extra which you haven't seen yet. If I go to the press and I hit department utilization, we can see how the utilization is growing and now flattening out. And we see that the capacity and time utilization are almost identical, which means that the equipment is being filled to its capacity while it's producing during its time. However, if we go back and look at the production graph, we see a problem. We see that WIP is starting to accumulate. Where is the WIP accumulating? Well, if we go back to the utilization as a function of time, it's either in the press or it's an electrical test. Now remember, electrical test is downstream, so it's going to take a little bit longer to fill it up. When we look at the WIP graph, though, it's very clear the problem is that electrical test. Let's go see how electrical test is trending with utilization. So if I go to index 29 and I hit the department utilization, and we can see we are headed towards 1. And when we see this play out to the end, and our WIP level has gotten very, very high at 634. And when we look at the utilization, we see that it got about 95%. And that isn't going to work. So that means we need another electrical test. This is a better second scenario, as shown. There's the production graph, and there are the utilizations. So in a similar way as scenario 2, we started out with the scenario 1 baseline, and instead of adding more of the first product, we added a second product, which is the medical product, and that routing is shown. And in order to double the amount that we wanted for the second product, or specifically to run to this schedule, we had to add just one additional tester, and we got a stable situation, and we got these results where the HDI product had a throughput as before of 15.36 panels per hour, and the medical product had 5.8 panels per hour. And you notice that the cycle time was affected by having the medical product, where it's 18.3 versus 11.58 for the medical, but originally it was 17.62 for the baseline for the HDI product. Let's run this so you can see what this looks like. And if we look at the WIP levels, we can see what product is running in each of the stations. Right now it's HDI we're looking at, but we can also look at the medical product. And if we pause, we can see that image. It's at step 4 and 19 of the HDI of the medical product. And if we look at the HDI product, it's step 35. What happens if you have the same demand, but you decrease the number of jobs that you release and decrease the number that's in a job, but you release it more frequently? This is the identical demand as before, but instead of releasing every 8 hours, we're releasing every 2 hours. Let's see what that looks like and what we can learn. And here we see the product running through, and we see the utilization, and we see the routing for the HDI product, and we see the routing for the medical product. And we also see how the graph is changing. And let's run that all the way to the end. And here is the result of scenario 4 with a smaller quantity every 2 hours. There are the throughputs. Notice the reduction in cycle time. There's something else I want to show you. When you look at the utilization of time, and compare that to the utilization of capacity and take the difference. And also, if you look at going to the press, the department utilization graph, we see that we're not utilizing all of our capacity. What that means is we don't need presses with as many openings. The same can be true in terms of drill. We don't need drill machines with as many spindles. We don't need solder mass bake ovens that are as big, nor legend bake ovens that are as big. In fact, as we get smaller and we scale to smaller size batches, we can become more flexible, have a lower cycle time with the same amount of throughput to meet demand. And this becomes a very big deal as you increase the quantities of different types of products with very different routings. So what have we learned from this? We've learned that the FASTAnalyst is scalable by any number of products. It is scalable to any number of pieces of equipment and configurations. It can identify bottlenecks. It can identify or validate capital expense opportunities. You can discover improved starts and plant policies. We didn't get into the plant policies, but for this particular plant, it was FIFO at each work department. You can discover product mix issues, and you can make global improvements instead of conflicting local improvements. I hope you found your time watching this demonstration of the FASTAnalyst useful.